the following algebraic equation. F of dx. In fact, that I got it in the first place. 2xt f of dx. So now it's a quadratic equation. It's no longer a function equation. This is a purely algebraic equation. Once again, you don't believe me? Go to Maple or Mathematica or do it by hand. Take this monster expression and plug it in. It's a complete routine high school algebra thing and prove this. Or you can go backward. Use a Babylonian quadratic equation. This is a quadratic equation and you get this either way. And this is obviously the solution is a formal power series. It's obvious because if you look at this, it starts with 1 and then it's self-referential, and by doing this operation like we did here, we can also generate this. QED, almost QED. Finally, what we're really interested in is the coefficient of x to the power 0. So it's a corollary. F of t0 is 1. So we get an explicit expression. X is 0 over t. An explicit expression. And finally, using the binomial, Newton's binomial, this is 1 minus 40 squared to the power 1/2. It's an easy exercise to get it 1/2 to n, blah, 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 to get it to the Catalan form, QED. So this is a new proof, I believe. Maybe not the nicest, but I believe it's nice. What's nice about it, that unlike all the other human elegant proofs, this can be generalized. First, no offense to Cardano, no offense to all these people who were obsessed with solutions by radicals. This was one of the stupidest questions to solve things by radicals. Then because there was a nice quadratic formula, minus a plus or minus b, blah blah blah, a minus b. And then Cardano did it for 3, and then Ferrero or whoever did it for 4, and then it was a big open problem that stumped people for 200 years, and then famously Galois and Abel proved these no things. Okay, but I don't think it's that interesting. Of course, it led to interesting things. It led to group theory. It led to lots of good things. I'm not saying it was a stupid question that led to lots of good mathematics. But as a question, it was stupid. Radicals, as you also said to Galois, is not the best thing. The equation is enough. There's another way of describing a function, and a computer can easily get it. So another way, okay, sorry, I got out of the head. But how did I get it in the first place? The cheating I got out of the head. Let me tell you how I got out of the head. And you crank out using this as an algorithm, you crank out the first 20 or 30 terms of this sequence, polynomial x. Then you have an ansatz. You have an undetermined coefficient. You guess that it is algebraic. It turns out that it's a general theorem that my former student Alvin Ayer proved, that a priori it's always guaranteed to be successful. There's always an algebraic equation. But that's not relevant. You just try, the computer doesn't mind, you just try a so-called ansatz. So in case of the Gauss, what he missed opportunity, it was a polynomial fitting. So now, here's I, f dx, and with a finite degree. So this is called an ansatz, an algebraic ansatz. So I crank out the first 30 terms of this, and then I look at the undetermined coefficient, and I want this to be 0. So I check it for the first 20 terms to get a system of linear equations. And Maple and Mathematica and MATLAB especially, very good in solving a system of linear equations. You solve it, you get it, and lo and behold. In this case, with 2, degree 2 in f, and degree 2 in t. So with 2, 2. So you only need 9 data points to get this. And that's how I could have gotten it. In fact, that's how I did get it. So the computer, completely from scratch, completely empirical, after you did this minor combinatorics, completely empirically found this. But how do you prove? I'm not done yet. Sorry, so far I did the guess part. Now the check part. This is not. This is still conjecture. This is, I didn't prove it yet. This was conjecture. That's equivalent to this. What I did prove was this. Yeah, I already told you. So you can also, you don't need this radical thing. You can directly operate with this equation, and everything is everything is an algebra. So any form of power series that satisfies such an equation has a property, it's an algebra. If you take another beast, G, with different one that have this equation, it's guaranteed that the sum is also algebraic. Also a product is an algebra. So in general, so then I go to the general case. Instead of the steps 1 and minus 1, I have a step capital S. And this method of guess and check works for any number of steps. Not that for this. So now let capital S be a general set of steps. So the same argument exactly establishes a function equation T sigma x to the power S, where S belongs to capital S and S is non-negative. So it's an arbitrary set of steps including 0. F dx plus sigma. Now if it's negative, we have to subtract the bad things. S is negative. T, you always have a T, because when you analyze a one more step, you have a T. X to the power S, but now S is negative. Now you have to subtract f of dx minus f of 0x minus the coefficient. So the f sub t of 0x minus whatever f sub tt. So if, for example, this is minus 3, you have to subtract the coefficient also, the derivative, and this. So that's a function equation. Once again, using function equation, you can generate the first 50 of 100 terms. And then ask the computer to guess such a thing. Having gotten a guess, how do you check it? You call the guessing g of tx. So you have a brand new thing. So you get a conjectured algebraic equation. So let its solution, which uniquely defines a certain from a partial g of tx, call it g of tx, and you want to prove that f equals g. So instead of proving that f equals g, a derivation, we do it the other way around, because we have a very famous rule in logic. Logic is not completely useless. The rule that if A equals B, then B equals A. A equals B, if and only B equals A. So I go backward. Instead of just trying very hard to find what f of dx, I guess a form for this and call this tentatively g of dx, and take this g of dx and plug it into the function equation. But it's easy to see that f of t0, everything inside here is a solution of another algebraic equation. So this is that a routine computable things in the so-called Zeilberger ansatz, or the algebraic formal power series. In fact, I know I have to actually compute it. I know by general nonsense that so you call this left hand side, blah blah blah, call it capital F of dx. I know the general nonsense, like I know that polynomial is a polynomial, polynomial times polynomial is a polynomial. I know that. If I have a polynomial of degree 1000, that polynomial of degree 2000, I don't have to multiply it, actually multiply it out to know it's polynomial. I know a priori it's polynomial. So this over here. So everything here is an algebraic form of power series, product, sum, algebraic form of power series. So I know they exist as certain algebraic equation. I don't want to see it. It's probably too complicated, but if I wanted to, somebody paid me for, I would get to. But frankly, unless you pay me a lot of money, I want to do it because I know it exists. So let's call this capital A of x. X is a parameter, so you don't make it t, and let's suppress the x. Capital f of t. And that can be written in f of t equals sigma ai j ti fj. But when you spell it out, it's equivalent to the coefficients satisfying a certain algebraic equation. In the case of Catalan, a sub n is sigma a sub I again minus 1 minus I goes to 0. So here, that's an example of the Catalan one. So that's equivalent to a recurrence of finite order. So if you know an upper bound for the highest I that shows up, that's a memory. This means if you check it to the first that many, if capital I is the biggest one, 0, 0, 0, 0, then rigorously it's 0 forever after. So since I know for sure that there is a cutoff, if I check it up to this, I know it's a completely rigorous proof. But in practice, I don't want to be bothered. I know that there is a way of doing it, so why bother? Just checking it for the first, I'm almost sure the 300 terms is way, way more than what you need. The actual I is an upper boundary I'm too lazy to do. I have an algorithm, but it will take the computer too long, and frankly, I don't really care. Because in this case, it's not worth the trouble. So the formula for this, and also another thing, the 2n should n, let's go back to the sequence itself, non-generating function. Is another famous theorem that is not hard to prove, that the sequence itself always satisfies a kind of recurrence. So the Catalan number is really 2n factorial over a factorial. This is, so what a factorial? A factorial is a stupid notation for a sequence that satisfies this linear recurrence with the initial condition. So this is a so-called holonomic ansatz. It's a complete description of n factorial. So similarly here, C of n is so C of n plus 1 over C of n. So that's another one. So this is a complete algorithm. For example, Fibonacci numbers are given by this recurrence with constant coefficients. So then the complete description of this sequence. So the computer empirically found this recurrence. In this case, the order is 1. So it's a to the power n equals some polynomial of degree 14, a of n minus 1 is order 20. The order polynomial of degree 14, 20. For the case of 1, 2, n minus 3, n minus 14, n minus 20. And this recurrence you can very fast compute as many times as you want. In fact, you don't need all the memory. You can, the memory here is only 20. You only need to retain a window of length 20. So as far as memory, not counting bit size of course, you have 20. So that's an answer. That's an answer, complete answer. And here it is. And I have a confession to make. This took 14,574 seconds on my not so good computer, but still. To get a fully rigorous proof of this will take maybe a month or 2 months. I know it's possible, but frankly, I don't care. It's not that interesting, and I think that's only a metaphor. Mathematics, we realize that lots of things are beyond the scope of humans. Still, humans like to prove. I went to the talk 2 hours ago. It was the worst talk I ever went to. But in some sense, in another sense, it was beautiful to watch a human get so passionate about something that to me, it's like, if you're not religious, you're really amazed that somebody can get so much into a religious text. So, so I can sympathize with this. So, it's a national enthusiasm. But it was really so Talmudistic what he did, and in some sense it was brilliant, because he didn't use a computer even once. He gave some methodology, some beautiful tools and results, and it was very, so in some sense it's nice. But this kind of mathematics, well, sooner or later, in 100 years, 200, will be obsolete, because it can only prove trivial things. Truly deep things like this, and of course, only a case study, it's only one example. This is only a metaphor of the future of mathematics. We have to abandon fully rigorous proofs, because by definition, fully rigorous proofs can only give us a relatively trivial knowledge. If you want to have really deep knowledge, we have to compromise. First, semi-rigorous or rigorizable. In this case, everything in principle is rigorizable. And later on, even give up this. And proving will be still a nice pastime. They will not be mainstream. Without a bunch of eccentrics, like some people who like to solve chess problems, it's still a nice hobby, it's respectable, but it's not mainstream chess. So similarly here, proving theorems will be just a nice occupation in 100 years. Thank you very much.